Okay, welcome to the Friday of the first week. Today we have two research talks, and first will be by Wei Zhu. He will talk about first order transition. No, was not the title.
Sorry, maybe I can introduce by myself.
Yeah.
Thanks. Very glad to have this chance to introduce our recent work here. Today, I'm going to talk about the complex FT. And I would like to propose a microscopic model to realize the concept of complex FT. So this is a general outline of my talk. In the first part, I would like to briefly review this concept, the complex FT. And this part of discussion, I'm mainly following the discussion in these two nice papers published in 2018. Okay? And the second part, I will show you our proposal about a lattice model, and I will show you how we construct this model and provide you some evidence that we believe that this model can realize the so-called complex FT. And this work was mainly done by Tang Ying from the Westlake University, and the collaborator includes Dr. Tang Qichen from the Georgia Tech, Dr. Ma Han, and Dr. He Yingchen from the Primate Institute. And this is the archive number for our paper. Okay. So let's start with the phase transition. Say we have a parameter in a physical system, H, that when you tune this parameter, you can induce a transition from one phase to another phase. And usually, we can define some kind of the order parameter to describe this kind of transition. Say you have an order parameter, say delta, and if this order parameter continues to evolve as a function of h and reduce to 0 continuously at the phase transition point, we can define this transition as a continuous transition. Okay? Except for this, there is another kind of the phase transition that widely exists in the physical system. Okay? So that is the first order transition. So in this case, you will see that the order parameter, say, experience a discontinuity jump at the phase transition point. Okay? So for the continuous phase transition, we know that it has been widely studied before. There were lots of famous theories there. In comparison, for the first order transition, I think first order transition received much less attention before. One of the reasons is that you know that for the continuous phase transition, people can ask that the question like, what's the nature of this transition? What's the effective theory to describe this phase transition? But for the first order transition, no one asks such kind of the question, right? So I think the common wisdom is that there is no general principle to describe or to explain how or when the first order transition will occur in a physical system. And the next, I would like to share with you some of the progress along this direction that may change your mind, okay? So the model we study today is called the Q-state pot model. You can take this model as a generalization of the well-known Ising model. So first, we need to define a pot spin first. Okay? So in this case, the Q equals 2. That means the pot spin can take two discrete values in the phase space, say up and down. Okay? Say up and down. And also, you can define, say, Q equals 3 state. That means equal local spin in phase space can take 3 different values, say 0, 1, or 2. And so on, you can define that the Q equals 4, 5, and so on. Okay? And the model that we write down, the original pot model is like this. Hj equals to minus I from 1 to L. This k is integer summation from 1 to q minus 1. Sorry. J, dagger. Okay, cross H, tau I, K. So here, I is a site index that describes a one-dimensional chain. So say like the one-dimensional chain. So I equals 1, I equals 2, and so on. So I is the index, K is an integer number, and here the sigma matrix is called the phase operator. That when you apply a sigma operator on a local port spin state, it just gives you a phase factor that depends on n. So here, n takes the different value for the port state. And here the omega is just a phase factor, depends on the number of q. Okay. And here the tau matrix is called a shift operator. That is when you apply the tau on local port spin state, it's just shift the spin by 1 modulo by q. Okay? So we can also express these two operators in the matrix form. If you express it in the matrix form, you will see that the sigma matrix is diagonal, and the diagonal element is like this. All of the other elements are 0. And for tau, it's non-zero for the sub-diagonal line, and all of the other elements are 0. Okay? And in this case, if you think about that q equals 2, that you will see that this sigma matrix will reduce to the sigma z of the Pauli matrix. And also this tau will reduce to the sigma x in Pauli matrix. Okay? And this model, port model, Q-state port model, when Q equals 2, it will reduce to the well-known transverse Ising model. Okay? And also you can find that these two operators satisfy the relation that if you want to change the sequence, that will give you a phase factor omega here. Okay? And one more thing is that for this model, this original Q-state port model, it has very nice properties. And here, one property is called the spin permutation symmetry, as mentioned by yesterday. Okay? So yes?
So you introduced this term, which is a cyclic permutation. Thank you. So your tau is a cyclic permutation. So don't you have a symmetry by the full permutation group? Are you breaking this down to ZQ, to the cyclic permutations?
Yeah, sure. I'm talking about this.
Okay.
Yeah. In general, this model has preserved the spin permutation symmetry. And in general, this spin permutation symmetry has many elements. So here I maybe take, for example, the Q equals 3 as an example. In this case, we know that for spin permutation symmetry group, only 6 elements. And they are generated by 2 operations. One is called the cyclic operation. Okay, we define the S as a summation of the tau. Okay, the tau operator. And here you see that when you apply this operator on the tau operator, it's environment, because this operator is defined by tau matrix. But if this operator apply to the sigma matrix, it will give you additional phase factor omega here, right? And then you can prove that if you apply this to the H0 matrix, it is the environment. That you see that when you apply this to the second term, it's environment. When you apply this operator to the first term, you see that the additional phase factor omega here was canceled by this. You combine this sigma matrix together. Okay? And another operation is usually called charge conjugation. Operation, we define this as C. So when you apply this charge conjugation to the tau operator, it just changes this tau operator to the complex conjugate, same as the sigma matrix. Okay? And also you can apply this to the Hamiltonian, and you will see that is the environment. Since here we have a summation k from the 1 to q minus 1. So in general, you can see that this model actually preserves the so-called the spin permutation symmetry group. Okay? And another property that is environment is important to our discussion is that the so-called duality properties. Okay? Actually, this is called the Kramer-Wannier duality property. That is, you can just change the operator to sigma operator to the tau operator. And also you can change the tau operator to the bilinear of the sigma operator. Okay, like this. Okay, when you apply this duality to H naught, you will see that under the duality property, it will change to the H naught, just to change the parameter H and J, so that you will see this Hamiltonian H naught is the environment under the condition H equals to J. So this is self-duality point of this model. So this condition is important because next we can discuss the so-called the phase diagram of this model, okay? Q-state pulse model. So for the phase diagram, say you have H over J, okay?
Is this duality the same one that fixes your B coefficient of epsilon with epsilon to 0?
Say it again, sorry.
So you have your B coefficient of with which epsilon appears in the epsilon of E. And this, well, at least on free state pulse is 0, and also freezing is 0. For 3 equals 5, I don't know, but is this the same duality?
Yeah, this duality is the same for general Q. Yeah, for general Q, yeah. So in this case, you will see, first you can think about that in the limit that H much larger than J. In this case, in this model, this 10 dominant, this is transverse 10 dominant, which preserves the eigenstate, ground state, as the ground state of second 10, right? So this 10 is actually a symmetric 10, that means symmetric phase, okay, which preserves the spin permutation symmetry group. Okay. In the opposite limit, H much less than J. Okay. The dominant 10 is the first one. So this is kind of the spin exchange interaction between the two nearest neighbor pulse spin. Okay. You can think about that this 10 will select a symmetry breaking state as the ground state. As you ask that, this is we call this is the symmetry breaking phase. Okay, spontaneously symmetry breaking phase here. And the next thing is that using these duality properties that you can argue the things like that if there is only one phase transition in between these two phases, okay? If there is only one phase transition in this model. The phase transition point should be located at this self-duality point, okay? If only one phase transition point, it should be located at this self-duality point, okay? So this is this phase diagram for this general Q-state pulse model. More interesting thing is like this. So this has been known from the 1973 by Boxer. Actually, the nature of this phase transition in this model depends on the number of Q. That for the Q smaller or equal to 4, this transition is continuous. Okay. In another case, for Q larger than 4, the transition is first order transition. okay? This is the first order transition for Q larger than 4. And especially we know that the nature of this first order transition becomes stronger and stronger when you increase the number of Q. Say, for example, we can make a table, say, for example, this is number of Q, and we can write the correlation length at the phase transition point. Say when Q less than or equal to 4, this correlation length divergent. By definition, this is for continuous phase transition, okay? For the Q equals to 5, this correlation length is around 2,500, okay? And for Q equals to 6, this is around 150. And for Q equals 7, this is around 50, something like that. So you see that for this first order transition, when you increase the number of Q, the correlation length monotonically reduces. Or you can define that the energy gap for this first order transition at the transition point becomes larger and larger. So this property will we will come back to this point at the end of this talk. You will see that, for example, compared to the 5-state Potts model, when you want to drive the 6-state Potts model to the real fixed point, you need to tune a larger parameter in the model, okay? So we will come back to this point later, okay? Okay, so yeah, after this discussion, next we briefly discuss the so-called the RG properties of this Potts model, okay? So for this model, we know that close to the critical point, there are some interesting operators that are our focus today. The first operator we defined as epsilon. So usually in statistics, physics, we call this is a thermal operator, okay? And another operator is sigma. Sigma is ordering operator. And these two operators are relevant operators. So today we just focus on space-time dimension equals 2 first, okay? In this case, these two operators are relevant operators. Except for these two, there is another operator we call the epsilon prime. So this is the focus of the talk today. And usually this is called dilution operator. So this operator, sorry. This operator is marginal operator, actually. So this kind of the information has been known for a long time. And actually, the RG property was first studied by Cardy in 1980, okay? So to study the RG effect, we can think about the problem within the conformal perturbation. Say you have some kind of the Hamiltonian, and this Hamiltonian can be expressed as close to a fixed point. So this fixed point described by some kind of the CFT, for example. In this case, we start with the Q less than or equal to 4 case. Study the continuous phase transition first, okay? So for continuous phase transition, you can think about the effective theory can be expressed as a fixed point under the influence by some kind of the irrelevant operator or marginal operator. Say you can think about it as this way, epsilon operator. And also you can think about to add this kind of the operator, but we know that these two operators are relevant operators. If you want to reach the fixed transition, you must tune them away, right? So we don't just, we just neglect this relevant operator in this effective model. And also you can think about it has many other irrelevant operators, okay? And at this step, you can write down the coupling strength, the RG equation related to this coupling strength, okay? And this RG equation will be like the epsilon prime A Q minus 4 plus up to the second order, okay? And here the A is a real positive number, okay? So through this RG equation, and immediately you can solve the fixed point. And here you see this equation gives two fixed points, plus minus, and equals to A 4 minus Q as a function of Q, two fixed points, okay? And this is a real fixed point, and this is defined in the case that Q less than or equal to 4, okay? So here at this step, we can plot a fixture here. So that is, say, this is the X for Q, okay? Say this is Q equals 2, Q equals 3, 4, 5, 6. And then this X is epsilon prime, okay? Coupling strength. And you see this, actually, as a function of Q, you can see this is a 2, 9 of the fixed point in the parameter space. We can just plot them like this. And for the integer case that you see, you can define a fixed point here, here. For Q equals 3, there are two fixed points here. Okay? So that means for the Q equals 2 case, this is the Ising model, right? And two fixed points, one of the fixed points related to the Ising CFT, as is well known, and another fixed point related to the tricritical Ising CFT, right? This is all minimum models. And also for Q equals 3, you will see that these two fixed points relate to the CFT, the three-state port CFT and the tricritical port CFT. And you see for these two lines that as a function of Q, if you think about that Q can be continuous tuned, you will see these two fixed point lines meet and merge together at Q equals 4, okay? Yeah.
But then why doesn't the beta function start with a term linear in G?
Linear in G. This is a coupling strength.
Yeah, but then d G epsilon dl would be something times G epsilon plus G squared. Like this is the generic beta function, no?
Oh, okay, so let me explain like this. So the first, this is a marginal operator. So usually the leading term should be proportional to the scaling dimension of epsilon minus 2 space-time dimension, right?
Yeah.
But this is marginal, so we don't consider this term. And due to this paper proposed by Cardi that this leading term, this constant term, actually proportional to Q when you study this model close to 4. The leading term actually is this constant term instead of this term.
Okay.
Yeah. So if I write the whole thing that think about the epsilon, you can write down the G epsilon coupling strength. Sorry. Okay. So this will be like the G epsilon minus 2 and plus G epsilon prime. G epsilon. So this is a leading term like this. And similar to sigma operator, like G sigma minus 2 plus, sorry, there is a coefficient here depends on the OPE coefficient and many others. So this is G epsilon. But we mentioned that we know these are relevant operators, so that the fixed point should give you that this G sigma equals 0 and the G epsilon equals 0. Mm-hmm. So that means in the effective model, we have to tune them away first, right? So here we don't consider these relevant operator, we just consider the influence of this marginal operator. And the leading term is this constant depends on Q. This is following the discussion from Cardi. Okay.
The way you wrote it, the fixed point should be a G epsilon prime equal to 0, right? It's the fixed point plus a perturbation. So I think that, like the line H equal whatever tells you that the fixed point should be a G epsilon prime equal to 0. And I think now you're shifting this. The G epsilon prime that you write later is some shifted version of that. It's not the same coupling.
Yeah, so this is because that, here, so this constant actually shifts the fixed point from 0 to non-zero, right? So this is...
I didn't understand, sorry.
Oh, sorry. Yeah.
No, could you repeat? I didn't understand, sorry.
So the reason is that previously we know that actually this epsilon prime operator is irrelevant in this case for Q smaller than 4 cases. But this operator will gradually become relevant when you tune the number of Q. And this operator actually will kill these continuous phase transitions.
No, I agree. I just say that I think that the G epsilon prime you're writing down in the last lines is not the same that you're writing in the first line. It's some shifted version of that.
No, I didn't. Which equation do you mention?
H equal H fixed point plus, no, G epsilon prime. H equal H fixed point plus G epsilon prime. That thing suggests that the fixed point is at G epsilon prime equal to 0.
Yes, so this gives to 0, and this gives the fixed point here, right?
Yeah, I think those equations are not consistent with each other, but I think it's a small, right, but one in, yeah, okay. I don't know if this
anyway,
is...
I can discuss you later.
Yeah, absolutely.
Yeah, so this is a very cluster paper, and you can just formulate this using the conformal perturbation.
Yeah, I agree.
Yeah. Yeah, okay, you can just think about that. You have some perturbation on this, like the final size effect, and talk about this Hamiltonian, like the not at the exactly at the fixed point, and consider it is a little bit away from it, and we consider how this coupling strength flow actually.
If the equations are consistent, then HFP is not the fixed point Hamiltonian.
Okay, okay, that's fine. Yeah. I just want to talk about that, think about that. You are a little bit away from the real fixed point and how this different operator will influence the flow. Okay. Yeah. So yeah, let me. Okay. You can. I'm sorry. Oh, A is just a coefficient, that is a positive number, real positive number. It is just a positive and constant.
Marco.
You can trust if it's A small. Sorry. I'm just wondering if it's important whether A is order 1 or small to trust this curve away from Q equal 4.
I don't know.
Because, I mean, if G epsilon prime becomes big, then you need to include further terms in that beta function, and you want... I thought the value of A was going to be related to some large correlation length later. Yeah, correlation length actually correlation length will have a function that depends on the Q. That you will see that this Q away from the 4, this will determine the larger and the small correlation length. But yeah. I forget the exact function for the correlation length. Okay, so if A was 10, you probably couldn't trust this away from Q equal 4 very much. I guess.
Okay. I don't remember this.
Okay,
one.
thank you.
Yeah. Okay. Okay. So yeah. So this is a case for the continuous phase transition. And the next, what I want to study and want to discuss is that for the case that is Q larger than 4. Okay, so this is our focus. And as we mentioned previously, for this model, in this case, actually the transition is first order transition. It's not continuous phase transition. And in these 2 papers in 2018, these 2 papers, that actually the authors proposed a very nice conjecture on the case of the Q larger than 4.
So what the conjecture is for this model, Q larger than 4, they assume that this RG analysis and this RG fixed point are the same, okay, for this case. Actually, this is assumption. In general, the RG analysis is based on the scale invariance. For the continuous transition, you can do this, but for the first order transition, you do not have the exact scale invariance. So that in principle, you cannot simply apply the RG analysis here. But the authors just conjecture that you can still apply, and they also assume that this RG equation are the same. If you accept this, they just make an analytical continuation at this point. That is, you do not have the real fixed point, but instead you will have two fixed points that is living in the complex parameter space, like this. Okay. So if I plot this in this picture, so that is, you can think about that. Here we need to say here we change this x as the real coupling strength, and we add a new x that describes the imaginary part of this coupling strength. And this fixed point will reopen here, actually in the complex parameter space. Okay? So that means in this case, you do not have the real fixed point, but instead you have two fixed points defined in the complex parameter space, like here. So this x is the imaginary part of the coupling strength. Okay? So, okay, and one more thing is that here you suppose that you accept there is some complex fixed point here, and the next question you can ask is that, so what's the effective theory for this complex fixed point, so-called complex fixed point, okay? And another conjecture made by these two papers in 2018 is, like here, we know these points are all described by CFT, right? And what the conjecture is, this point here actually are also described by some kind of the CFT. But this kind of CFT is not a conventional one. They call this is a complex version of CFT. Okay. So next, I would like to briefly mention this concept about the.
Could you explain the definition of the theory at G epsilon prime equal to 0? Since you're not doing conformal perturbation theory around the fixed points, I just didn't know what your definition of the coupling is.
You mean the QX4?
No,
right?
the horizontal axis. What's the definition of the theory that you begin with at G epsilon prime equal to 0? How is that theory defined?
Okay, so for let's talk about the Q less than 4 case. That would be easier. So for these 2 points, these are minimum model for QX2 and 3. And for all of the other points other than this integer value are some kind of the irrational CFT.
I thought you were starting from a non-fixed point. That was your formula above. Your G epsilon prime equals 0 is not a conformal fixed point. I was just wondering what the definition of that thing is.
I see. So.
I mean, if you do conformal perturbation theory, I have no issue. But I thought this plot is, you're not expanding around the CFT, right? So I was just trying to understand.
Yeah, I only know this point. These are these fixed points are kind of the CFT related to.
So is the definition of the coupling G epsilon prime is actually through conformal perturbation theory?
I'm sorry?
I just didn't understand what your definition of G epsilon prime is. Because I didn't know what your starting point is.
Oh. G epsilon prime is some kind of the contribution that just describes the.
Yeah, but I don't understand your HFP because HFP, as you were saying earlier, is not actually the fixed point.
Okay, so let's say like this way. So say you can start like this point, Q equals 4. We know that this operator is exactly marginal. Okay. So that this fixed point, you can think about like describe the Q equals 4.
Right.
And then we know that we try to discuss that the Q less than or larger than 4. So we add this epsilon prime operator based on this fixed point.
Oh, I'm not sure if that's unambiguous, but I'll ask you later. Thank you.
Okay, yeah.
I mean, I think this epsilon prime operator is from tricritical Ising and tricritical poles. No, but you just rewrite the conformal perturbation theory from this upper blue lines to just shift the coupling a little bit. It's a rewriting.
S4 is a symmetry. So epsilon prime cannot change the symmetry that you have. So if you have S4, you cannot describe the point S3 by adding a singlet of S4. So the RG exists, the RG flows, they live on lines with the same Q. So I think that what this G epsilon prime is would be you start from the tricritical point and then you flow down. Now, I think that this G epsilon prime is actually just a shifted version of this. So like in perturbation theory, instead of saying that one fixed point is at 0 and the other one is at epsilon, you say that one is at minus epsilon over 2 and the other one is at epsilon over 2 because you shifted the coupling. I think it's well defined in perturbation theory and probably not otherwise. So close to Q equal 4, it should be fine, I would imagine, but probably not for, Q equal 2, for example. You always start from one fixed point. All of this is like this thing is under control when you're close to Q equal 4. You should start from one of the two fixed points, and then you just shift the coupling, and that's your coupling is now G epsilon prime is G epsilon prime minus something.
Okay, thanks. So, yeah. Okay, so I just talk about a little bit on this complex FT first, the concept. So, usually, traditionally, actually, when this FT can be classified into the unitary and also non-unitary. These two. And how we define this unitary is defined as for the safety state. Their norm are all positive definite, right? Positive number. And if you have one safety state or some of the safety state has negative norm, we define it as the non-unitary safety, usually. So say you can think about that you have a safety state, right? First you can calculate the norm like this. One of the norm like this, right? And then you will have this will equals to, say, I think this 2NH plus like this, right? Okay, and then you will see that the first condition, you just simply think about the central charge. When central charge is less than 0, so you will see this norm will become negative for n goes to infinite notch, right? And also for this condition, you will see that if the conformal dimension, it becomes negative, this norm should become negative for n equals to 1, right? So in this, you can check the different norms, the norm of all of the safety state in the tau structure, right? In general, you can think about that when central charge and the conformal spin will give you the classification about the utility of the safety. So here, for example, we can make it for the scaling dimension and for the central charge. Okay. For non-unitary CFT, we know there is at least one related to the negative, and the central charge will relate to negative. So that means here we add a word that is or, right? So either central charge become negative or the scaling dimension become negative, it will define a non-unitary CFT. Okay. Or you can take this as a necessary condition for definition. It is hard to make a table to include all of the cases. For unitary CFT, by definition, we think about the scaling dimension and the central charge are all positive. So here I add a word, this is the end, right? I'm sorry? The complex.
Sorry, I thought generically in these like complex CFTs, the scaling dimensions become complex. They're not just negative.
Yeah, I know. I will talk about later. Okay. So this is the traditional what we know, right?
Oh, because I thought you were saying it's like necessary, and I thought.
So here I just try to make a comparison. Give me 1 minute. I will go to that point. Okay. Okay, and also you can ask, for example, the other conformal data like OPE, right? In general, we define the OPE on the real, right? And also, one important thing I think is the safety state. Yeah. Yeah. Compared to, you mean for high dimension, you just compare it with the unitary bound, right? From below. Yeah, but the set of scaling dimension, you say can be negative, right? I'm asking you, do you want it to be coming from below or not? I just think about from this simple condition for two-dimensional case. The set of all operators that you want to include in your theory, the scaling dimension is supposed to be coming from below or not? I just need at least one of the. That's not my question. My question is whether the set of scaling dimension is coming from below. Because if it is not, why would you believe OP would converge? Or why should OP be optimized? Oh, sorry, I didn't get what the set of the. Sorry, I didn't get
the collection of all operators of the theory.
Sorry, I don't know. Sorry. Yeah. Yeah, this is what I want to say a little bit later. Sorry, I didn't get your point, maybe, yeah.
Well, my point is that it's not clear to me that outside the context unitary CFTs, the OPE even exists, let alone talking about what values OP coefficients should take. Sorry, can you, what?
And then just say that because the OPE doesn't exist, you would need to specify all higher point functions as well, and the scaling dimensions and 3-point functions would no longer be enough to specify a non-unitary CFT.
Sorry, I didn't hear the first part of your statement when you had the mic.
If this is no longer a statement about OPE coefficients, but about 3-point function coefficients, then I think everything is consistent.
Yeah.
Okay, thanks. Yeah. Yeah. For the unitary CFT, we know that the CFT state is just left and right state just connected by the simple conjugate. But for the non-unitary CFT, we know this, we don't have this simple relation with each other, right? And for the model, that we know that for unitary CFT, say for example, the ports, model Q smaller than 4. We know this minimum model, that is unitary CFT. For non-unitary CFT, one known example is Yang-Ni model, that is central charge takes the negative value here. And so-called complex FT means that here, what we want to do is just to extend this definition about the conformal data to the complex plane. That is, in this case, we allow the scaling dimension, choose the complex value, and also the central charge relates to the complex value, and the definition of the OP coefficient become complex. And the same with the unitary CFT, here we know the left state and the right state are not the same state anymore. They are two different states. For non-unitary system, in general, you need to define the left eigenstate and the right eigenstate separately, okay? And of course, here you may ask a question that if this kind of the complex CFT indeed exists, so what kind of the microscopic model can realize this kind of the CFT, right? So this is the question that we addressed, and I hope to share with you our proposal that I hope to see that at the end of the talk you can accept that the so-called the Potts model when Q larger than 4 indeed realize such kind of the complex FT. So this is our proposal. So next, I would like to share with you our model. We call this is non-hermitian Potts model. So this model in general contains two terms, H0 plus H1. And H0 is the original Potts model. We already write it down. And we add a new term, H1 here, H1 K1 and the K2 summation from 1 to Q minus 1. And here this is tau I K1. Okay, so this new term involves 3 spin interaction term in this H1 Hamiltonian. Okay, so let me next share with you some idea how we construct this H1 model. So first, we can make a table here. So the H1, not H1. So previously we mentioned that this H0 preserves the duality properties if we take the J equals to H, right? And also it preserves the spin permutation symmetry, okay? And next we can show you that the H110 actually preserves these duality properties, okay? So here, for example, we know that this duality transformation is changed the pair of this sigma spin to this tau, and change the tau to the sigma dagger, sigma, like this. For example, we can check the first 10 here, right? The first 10, and you may check this first 10 under this duality transformation will change to the fourth 10 here. Like this. And so on, you can check 10 by 10, and you will see that this 10, H110 in total, will preserve these duality properties. Actually, this is very important when we discuss the phase diagram of this model, as I show you below. So another thing is that we can prove that this H110 also preserves the same spin permutation symmetry as H010. So you see that when you make the cyclic operation on this sigma operator, the phase factor was cancelled by this bilinear 10, and also the tau 10 is the environment on the operation. Okay? So you see that H110 actually share almost the same properties as H0. So what's difference is Hermitian property. H010 is a Hermitian operator, and here we would like to introduce the H1 Hamiltonian break these Hermitian properties by introduce that lambda coupling strength as a complex number, okay? As a complex number. So this coupling strength is a constant, the coupling strength, and we would like to choose this coupling strength as a complex value. Okay, so the motivation to do this is like that we can think about that for the complex Ft. So since that we know if you allow the central charge, say, to be the complex value, you can think about the Hamiltonian of this model should be non-Hermitian Hamiltonian. So this motivates us to introduce a new 10 actually to break the Hermitian properties and try to search for the so-called the fixed point in the complex parameter space. Okay, so next here for this new Hamiltonian, if we set this
can I ask you a
J10
question?
as a
Sorry. So the only breaking of hermiticity here comes from lambda complex, the rest of the Hamiltonian. So why not just, so another compatible choice would have been just to put a lambda or to make J and H complex, say, in
good
the first
question,
one.
but I need some more time to answer this question.
Okay.
Yeah, okay, I will come back to this point.
And maybe I can ask another one just, but also maybe that comes later. So if you take lambda real and you take Q less than 4, is this Hamiltonian any relevant deformation or what is it, this addition?
I don't know.
You could have,
I didn't
you
try.
could have added it, right, in general.
For Q less than 4 case.
Yeah. So
I don't know.
Okay.
Sorry, I don't know. Yeah, so next I will focus on, for example, Q equals to 5 in the yeah. Okay, so next I set, for example, the J equals 1 as the energy unit. You will see you have 2 parameters to tune. One is H, one is lambda. Okay, but lambda is complex. So if I plot the parameter space of this model, so this is H. So sorry. So let me plot H along this direction. So H. So we know H large limit. This is a symmetric phase. So H in the opposite limit is a symmetry breaking phase. And the phase transition point is at HC equals 1. This is the self-duality point, as we mentioned above, for the original pulse model, the phase transition point located at this point. And next, we introduce the lambda parameter in this system. So I plot this as the imaginary part of the lambda parameter. And this is the real part of the lambda parameter. So in general, we have 3 real parameter in this model, okay? And importantly is, so we can define, so this plane defined by the condition for HC equals 1, this is the self-duality plane, okay? So originally, so this point is the self-duality point. After we add this lambda 10, it becomes a self-duality plane, because the H110 preserves the duality properties. And the same argument as before, so that think about when you tune H, transverse field 10, if there is only one phase transitions between these two phases, if there is only one. So this phase transition point should located on this self-duality plane, right? So this condition will actually reduce the computation in the search of the fixed point on this in the parameter space. Okay. Okay. So next, I want to share with you that in this duality plan, I indeed located 2 parameter point. We call one is the lambda C, and another one is the complex conjugate point. And they all have the finite negative, finite imaginary part in the coupling strength lambda. Okay, and these 2 points can realize a so-called the complex fixed point. So how we determine this fixed point is like this. So we think about that. We know that if they are indeed the CFT at this fixed point, and all of the other point has a finite energy gap, that is first order transition, we expect that these kind of the, say, these kind of the fixed point should satisfy the energy spectrum at this fixed point should satisfy the prediction from the CFT, right? And the leading term comes from the fixed point, and the higher order term comes from the finite size effect for the finite size calculations. Okay, so here, what the only difference from this case to the previous case is that for these eigenvalues for the energy gap here, this is a complex value. It has the real part and the finite imaginary part, because and also the scaling dimension should be a complex number. Okay, and in this case, when you construct the cost function to search for this fixed point, you need to consider the fitting for the real part and the imaginary part together. Okay, and for this, after you locate these 2 fixed points, and then you can determine what is it really a CFT or not, right? So what we did is just we define a so-called the rescaled gap, say like this. So we believe this, we remove this prefactor, non-universal prefactor, and to get the scaling dimension here. And from this rescaled gap, you will see that these will have the so-called the conformal tower structure in this model. That is, the descendant field has the integer spacing with the primary field. Okay, this is the signature of the emergent conformal symmetry at this fixed point. Okay. This is how we determine that this fixed point and it has the emergent conformal symmetry at this fixed point. If so, so next we can use the so-called theta operator correspondence to extract the so-called conformal data that for this complex fixed point. Okay, so let me make a table to show you the conformal data. So that is, this is the operator. Sorry. So this is the operator. Say epsilon, epsilon prime, epsilon prime prime, and sigma, and many others. Say this is scaling dimension from our model. Okay. Let me use the data. Yeah, this is the numerical data for here, so for the model. This is numerical exact diagonalization. So we just get the low-lying spectrum and rescale it, and to find the gap.
So it's not Hermitian matrix, but diagonalizable. That's a property of. Is it obvious?
You can numerically diagonalize it, get the eigenvalue, but the eigenvalue become complex in this case.
Yeah, so it's not a generic property of non-Hermitian matrices, right, to be diagonalizable.
Yeah, but numerically, there are some method based on the original Nansel's method. You can improve it to apply to.
I'm talking about just linear algebra. Like it's. Okay, so it's just. I'm just asking if it's an extra constraint you put on the deformation, or if it just comes out that it's okay. I guess it's okay.
Yeah, it's okay. I think that.
Yeah, you can bring it in general, but
sorry, can I ask what? Is there a constraint on imaginary part of the energy? Does your imaginary part of the energy have to be negative so that you have decaying excitations or something like that?
No, actually, this is just a numerical problem. If you just want to, you can, for general non-hermitian Hamiltonian, if you just want to target the several eigenstate, you have some controlled way to get that.
But then I would typically think about those as some kind of excitations that are going to blow up eventually. They're just going to exponentially grow and.
Yeah, I understand that. So you still have some numerical way to extract that. I believe so. Yeah.
Thank you.
We didn't develop the numerical method here, just to use the well-known algebra here. So.
States do you keep in the numerical, in the exact diagonalization?
You mean the energy level?
Yeah, how big a matrix that's being
How big is the
diagonalized?
matrix?
Yeah.
So the current largest system size we study is 13. And for the Q state, five state postmodel so you can largely imagine this is like this number. But we can use some symmetry to reduce the Hilbert space.
Thanks.
Okay. Okay, so this is the operator that's relevant to our study. So sorry. So epsilon prime 1.908. And this is 4.38. Sigma operator. Okay, so in total, we can identify 13 primary operators. I think the most important feature is here you see the scaling dimension actually is complex number with a finite imaginary number, okay? And also, what we did is also compare it with the analytical continuation. Previously, we mentioned that for the fixed point, you can do the analytic continuation, and for Potts model, you can base down the analytic solution for the real case and do the analytic continuation. In this case, you can get some more numbers, and these are also listed them here. Sorry. So this is 0 point. So you will see that compare them together, these two are almost agree with each other quite well. So in this case, this drives me to think about that. In this model, in this case, the analytic continuation is somehow like exact, okay? Almost exact. Okay. And then at this step, we can come back to answer your question that you can think about here. So here we can define that, so-called relevant operator in this case as the real part. If the real part is smaller than the space-time dimension, we call this is relevant operator, okay? So in this case, you will find that we have three operator, relevant operator, epsilon prime, sigma. Actually, this is why in previous discussion we consider these three operators. And for the contribution to the Hamiltonian, this is sigma is the vector operator. So this is different, symmetry is different from the Hamiltonian. So when we discuss the contribution to the Hamiltonian, we only need to focus on these two. So epsilon and epsilon prime, okay? So for epsilon operator, we know that this is somehow like the local operator content, sorry, IK is like this. So this is the local operator content for this epsilon operator. The most important thing is this is a negative sign here. So please note that for the original model, so here this sign is positive. That means this epsilon operator has a different duality as the Hamiltonian. because you can think about when you change this sign in this phase. Suppose that you are located at this duality plane. If you add this epsilon operator, it will drive you to either this way or this way. This is a relevant operator, breaks the duality properties. Okay? So in this case, you see this operator is duality odd. Okay? So that's the reason why that you can think about that in this model, when you tune the parameter h, is actually tuning the contribution of this epsilon operator to the Hamiltonian. So only at this duality plane or duality point, this epsilon operator is forbidden. Okay, so that you can drive a phase transition, right? Okay, and more importantly, besides this epsilon operator, you have another operator we call epsilon prime operator. Actually, epsilon prime operator is duality even. And also, this is SQ even, okay? This is a scalar operator, also preserves the SQ symmetry. And importantly, you see this operator is complex operator. So that in this case, you can think about in the Hamiltonian, when you tune the parameter lambda, is effectively to tuning the contribution of epsilon prime operator to the Hamiltonian. So if you can tune lambda to tune this operator away so that you can reach the real fixed point as we plot here, right? So in this case, you can think about, since you have two relevant scalar operator, that is epsilon and epsilon prime. So tuning h is effectively tuning the contribution of epsilon. And tuning lambda or h1 can effectively tune the contribution of epsilon prime operator. Only at some point that you can tune this epsilon prime operator away so you can reach the fixed point. And the difference is that the two relevant operators, but they are complex, so that you have to tune some non-hermitian Hamiltonian. And following your question previously, so that you can understand, so that if you just say, for example, change the h to the complex number, it does not help because this does not contribute to the epsilon prime. It effectively tunes the epsilon operator in the Hamiltonian. So you cannot reach the goal of the complex fixed point. So this is the way that we think about this problem. So that's how you can construct this model. Yes?
Just to remind that we are a little bit over time. Just if we can close the discussion in 3 minutes or 5, that would be great.
Maybe I should not proceed.
Okay, thanks.
Okay, so yeah, so maybe I can have 2 minutes to make a conclusion, okay? So here, at this step, so the last thing is that you may ask the question, so is there any more example or not, right? So I have to say, so the previous calculation is based on the 5-state Potts model, okay? So next thing is that we can try, for example, the 6-state Potts model, for example, okay? If we plot a picture here, say this is Q, for the dimension, space-time dimension equals 2. This is 2, 3, 4, 5, 6. So continuous phase transition point, I use a circle here. And for the original 5-state Potts model, 6-state Potts model, we know this is first-order transition. And as I show you above that, actually we believe this first-order transition actually controlled by the so-called complex FT. And the same strategy you can apply to the 6th Potts model here, and we have the evidence to support that this has almost the same story. The only difference is that in this case, the weakly first-order nature becomes stronger, so that you need to tune a little bit larger parameter to reach this complex fixed point, okay? And another question you can ask is that this is 2-dimensional case, and people are interested on the higher dimensional case, say for example, 3-dimension. We know for 3-dimensional case, this point is the icing transition, it is continuous transition. But for the 3-state Potts model, we know this is the first-order transition, right? And so you will know that there is a critical line that is QC, like here, right? For 2-dimensional case, this QC equals 4. But for 3-dimensional case, this QC is around 2.7. So three-state Potts model is actually a first-order transition as we known before. And currently, we have some evidence to support that this three-dimensional three-state Potts model is still controlled by the complex FT. What we did is based on the so-called the fuzzy sphere regularization. As you know, previously, at this point, for three-dimensional Ising transition, we proposed a method based on the fuzzy sphere to construct this three-dimensional Ising transition, and then we can identify the emergent conformal symmetry here. And what we did here for the Potts spin, that we, based on the fuzzy sphere, we just extend the definition of Ising spin to the Potts spin. And then you can realize the transition and analyze the fixed point properties. And we believe that in this case, the three-state Potts model in three dimensions is controlled by the so-called the complex FT also. Okay, so you can ask, you can consider that maybe this is an awful Potts model, right? And you may ask that, is there any other examples? Very recently, so we try to use the fuzzy sphere method to study the two-dimensional, the so-called SO5, the DQCP problem. And this is a transition from the near to VBS transition, okay? And based on the fuzzy sphere, first we can construct this transition, and it can realize a phase transition like the UN and UK. These two parameters controls the VBS order and the valence bound solid state. And this line is this is the near phase. This is the VBS phase. And this is SO5 transition line, okay? Okay? And along this line, we found the evidence that approximate conformal symmetry emergent here. And then we can extract some of the conformal data along this SO5 transition line. So here, due to the time reason, I just list a table to show you the results, what we have here. So this is the fuzzy sphere calculation. So this is the RCAF number. This is 1, 6, 3, 4, 5. What we get, the operator is delta phi, delta t, delta s, delta j mu, and delta m4. So we identify 5 primary operators in the spectrum. So phi is a vector. This is a SO5 vector operator, which controls the SO5 symmetry spontaneously breaking or not. And T operator is a symmetric rank 2 tensor, which controls the near to VBS transition. That is, tuning T operator is effectively tuning the near to VBS transition. Okay, and this JMU operator is a flavor current because this is a continuous symmetry. You have a current here. And M4 is a 8-pi monopole operator here. And we identify the scaling dimension. This is 5 point, and this is 1.4. And this is 0.84. This is 2, and this is 3.8. Okay. In this case, you see the 8-pole monopole operator is indeed irrelevant, so that you can have this phase transition. And most importantly, we identify that there is additional, we believe this is a relevant scalar operator. And if I make an analog with the Potts model that we proposed above, this operator is somehow like the sigma operator. This is a vector operator. And this T operator is somehow behaves as the scalar epsilon operator. But in two-dimensional case, we have exact duality properties, so that you can use the duality properties to control the contribution of this operator to the Hamiltonian. But here, for this model, we don't have duality, but you can apply the SO5 symmetry to tune this operator contribution. But for this operator, this is scalar operator. This is very much like the epsilon prime operator, as we discussed above. And we believe appearance of this operator, scalar operator in the Hamiltonian will drive the system to the so-called complex CFT. And also, if I make a comparison, so this is another numerical bootstrap calculation based on the SO5 CFT from the Ning Shu. What he gets, the data here is actually very close to what we calculated here. So this is 2.359, this is 5.8, this is 2.3884. And 2 months ago, there is another paper based on the Monte Carlo calculation that is on the JQ model. And what they get, the data here, also close to our results. This is 0.27, and this is 1.71. This is 2. Yeah, so the data currently are almost consistent with each other, but I have to say the physical conclusions are different. Currently, based on our explanation, we believe this operator will drive the possibility of the complex CFT in this system. So this is our answer for these near-Webius transitions. Okay, so here, just to make a summation, we believe the model I present here realizes the so-called complex CFT. Okay, thanks. Yeah.
Okay, thanks a lot. There have been many questions, so maybe we can bring all the questions to the coffee break. Let's thank again Wei.
Thank you.